Hello, I'm Alex, and welcome to this new series of videos where we are looking at the grade 9 academic course based on the Ontario curriculum. Links to that curriculum is down in the description. That course is called the Principle of Mathematics. We are starting with the first section in the curriculum, number sense and algebra. Today is the first lesson called the Introduction of Exponents. You might be asking yourself, what is an exponent? An exponent is typically of this form, with a base, which I've called big B for base, and the superscript a, like a little a up top in the right. That a is often referred to as an exponent. Sometimes it is referred to as a power. If we said this out loud, we would say that we have b to the exponent of a, or b to the power of a. As a side note, sometimes this entire thing will be referred to as power. I'm going to try to avoid that, to avoid confusion. Let's start with some examples. Here, we have 3 to the power of 2. There's a short form for many numbers. In this case, we would say 3 squared. Anytime we have a power of 2, we can replace that by saying squared. A similar one would be 5 to the power of 3, which we say 5 cubed. There's many more past this, but they're less known, less used, and so usually we only use squared and cubed. Another way we can say it is we can say x to the 4th power. The term power here can be dropped. You can say x to the 4th, or you can keep it with what we already know, as in this last case, where we have 1 to the exponent of 1,337. Now, what type of numbers can we use in an exponent? Well, let's start with the base. The base can be any real number. This can be any number that you can think of, as long as it's not complex. You can take complex numbers, but I'm going to assume you don't know that yet, because I didn't learn that until university. There will be an aside at the end of this video talking about the types of numbers. This isn't necessary, you can skip it. But if you want to know a little more, feel free to stick around. So a real number is basically any number you can think of. That could be 1, 2, 3, -1, -2, 0. It can be fractions, a third, a fifth, 36 over 41. It could be a decimal. It could be 1.1. It could be 1.13567428946, whatever, repeating, I don't care. Something that goes on forever. It could be pi. It could be Euler's constant, if you know what that one is. Any number you can probably think of, it's probably a real number. For most of our examples, we're just going to be working with natural numbers because they're easy to kind of work with in our head. As for our exponent, we're going to start with natural numbers. A natural number is basically, you can think of them as the numbers that you learn when you're a baby. 1, 2, 3, 4, and so on. You don't start at 0, you only start at 1, you go up. We're going to use that base throughout this video and the next video, and we're going to find out what it means to have integers. Our integers are 1, 2, 3, 4, and so on, but it also has 0 as well as those negative counterparts, -1, -2, -3, and so on. So on to our first definition. Exponents are repeated multiplication of the base a number of times equal to the power. I've also noted that we're just looking at natural numbered exponents here. There are some cases where this works out for other types of numbers we use for exponents, but of course right now we're just working with natural numbered ones. So in a general term, if we have b for base to the exponent of a, b to the a, we have b times b times b times b times b times b times b a number of times, so that there are a total number of b's. It's not a number of the multiplication symbols. It's the number of these. So if it helps, you can think of it as there's like an imaginary 1 there times b times b times b times b, so that there are those a multiplications of b. But if you just count the number of b's, it should be a total of them. So if we go into some examples, some that we saw just moments ago, 3 squared is 3 times 3. There are 2 3's. 3 times 3 is 9. That's an easy one. 5 cubed is 5 times 5 times 5. There's 3 5's there. 5 times 5 is 25. Times 5 is 125. Now you might be excited about this one with the big exponent. 1 to the power of 1,337 is 1 times 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 1, and so on until there are 1,337 ones. However, 1 times 1 is 1, times 1 is 1, times 1 is 1, times 1 is 1, and I think you get where this is going. This is just 1. That's all for today's video. Like I said earlier, there's going to be a slide on the categories of numbers if you're interested. It's not necessary for the course, but it's still sort of the kind of fun thing you might want to learn a little more of. If you're not sticking around, thank you so much for watching. Like and subscribe if you want to see more of this content. Tell me what you liked, tell me what you didn't like, tell me what you'd like to see more of. I'm hoping to create more of these lessons throughout the grade 9 curriculum, reaching the grade 10 curriculum, and we'll see where we go from there. I'm hoping to pair each video with another video where we just focus on going through some examples for some extra help, some tips on problems you might come up with while you're doing your homework and whatnot. So if you're not sticking around, thank you so much for watching. I'll see you next time, hopefully. I'm Alex. Bye. Now, if you are sticking around, this is the aside for today on the categories of numbers. Now, we've already seen a couple of these categories, namely the natural numbers and the integers, but I've kind of described them a little more clearly here. So here are the natural numbers, which is this n with this second bar going down. And this is what we call set notation, these little curly brackets. This just defines a group of numbers. There's no operation between these numbers. This is just to define a group of them. If you ever want to refer to that group, we can just say, hey, the natural numbers. So the natural numbers are 1, 2, 3, 4, and I use this ellipses to implicate that there is a pattern that you can follow, and you can probably see the pattern here. The pattern is just you add 1 each time. The whole numbers are just the natural numbers, but you start at 0. The difference here is, of course, a 0, but sometimes when you're referring to these sets, you want to make sure that you don't have 0. If you're dividing by a number, and you're saying, I can divide by any number that's part of this set, you might want to say that that number is part of the natural numbers, because I want to make sure I never divide by 0. The integers, like we said, are like the natural numbers. They are the 0 and the 1 and the 2 and the forever on, as well as the negative counterparts, the -1, the -2, and forever on going this way. The irrational numbers, which is this fancy Q with a stick through it, is a set of A over B, these fraction pairs, such that A is an integer and B is a natural number. And remember that B we're saying is a natural number because natural numbers don't have 0. So this way we never have to worry about dividing by 0. Our real numbers are difficult to define. Like I said earlier, they're probably about any number you can think of, as long as it's not a complex number. If it's a complex number, it's not a real number. Our irrational numbers, there's no fancy symbol for this one. It's just the set of reals without the rationals, hence the irrationals, is a set of A, element of the reals, such that A is not an irrational number. So this is just basically any number you can't define as a fraction. So no 1s over 1s, 2s over 1s, 1s over 3s. They're always going to be they're always going to be an infinite decimal expansion, as long, again, as it's not a fraction. So 0.333333 continuing on forever can be written as 1 over 3. So that is actually a rational number, despite the fact that it goes on forever. However, numbers like pi, which is 3.1415 and so on, are in fact irrational. They go on forever and they don't have any way to define them as a fraction. Complex numbers, as I've alluded to a couple times throughout this video so far, are way beyond the scope of this course or any course you'll probably be taking within the next couple of years. However, we can write them as a plus ib, where a and b are real numbers, and we define I, this little 3 equal sign is kind of what we use as a define. We define I as the positive square root. Remember that a square root has a positive and a negative part. The positive square root of -1. And you might be thinking, wait, you can't take a square root of -1. And you're right. In real numbers, in complex numbers, we assume we can do that. And we just say whenever we're taking a square root of -1, we just call it I. Anyways, that's it for this aside, and that's it for this video. Thank you for watching. And like I said earlier, if you want, like. If you're interested in watching more of this kind of stuff, subscribe. Let me know in the comments what you like, what you didn't like, what you want to see more of. If I come up with that example video, there will be a link to it in the description. Thank you so much for watching. I'm Alex. See you next time.